Okay, welcome to the last lecture by Sylvain. And yeah, we are almost all here. So we will finish as usual. The lecture will last 1 hour 15. So please, Sylvain, take it away.
Thank you, Francesco. Good morning, everyone. So I'll first start with reminders, of course. Reminders from the CFT, from the Bootstrap approach, before trying to make a link with the statistical definition of these loop models. So in the CFT, essentially the basic axiom is the existence of some degenerate fields. And then we are considering all possible non-diagonal fields or diagonal fields that are compatible with these degenerate fields. And we obtain a discrete spectrum of non-diagonal fields in particular. So writing everything that's consistent, I mean, this is what we would call a extended spectrum S tilde. Now, if you take a particular statistical model, you won't find all these fields in your model. Typically, we'll find a subset. And here, I've written this subset in the case of 3 particular models, starting with the ON loop model. So in the ON model, you have only part of the degenerate fields. You have basically all possible non-diagonal fields, and that's it. Then there is the UN model, which is maybe a little less familiar than ON, but it's a simple variant of the ON model, where instead of a real vector, you just consider a complex vector. And this has the effect of restoring all the degenerate fields, but killing half the non-diagonal fields. So now this R has to be integer instead of half integer. And then there is the Potts model. So the Potts model has a discrete symmetry group, SQ, the symmetric group. And it is in fact very similar to the UN model. You just have to remove a few non-diagonal fields. So you remove the non-diagonal fields with R equals 1. But instead you add a series of diagonal fields here whose momentums are of this type, P0S with S half integer. Okay, so I'm not justifying these formulas, but I'm just saying what the known spectrums of these models are. And when you think of it, maybe the most remarkable thing is that there are coincidences between these spectrums. I mean, if you were in 3 dimensions, probably you would not expect some conformal dimension in the Potts model to be related to a conformal dimension in the ON model. But here we have a huge number of coincidences of conformal dimensions between these 3 models, which look a priori quite different.
Say just a couple of words of why do we know that this is the spectrum of these models? Where does that come from?
So originally it comes from modular invariance of partition functions, which were computed already in the 80s. Okay, so
Sorry, but modular invariance, of course, is a very general property. How do we know that one is the ON, one is the UN, one is the Potts?
Right, so in fact, the partition functions were originally computed starting with the lattice models and taking the critical limit. And then they found that, it means Di Francesco, Saller, and Zuber found that the result were modular invariant partition functions. Well, of course, in fact, they are already modular invariant on the lattice, and then this is not spoiled by the critical limit. And the difficulty was to decompose them into characters. But okay, this is a bit tricky, but they did that. Okay, so, yeah.
The spectrum you wrote here corresponds to the dilute phase or dense phase?
Well, it corresponds to both. In fact, I mean, you can go from the dilute phase to the dense phase by inverting beta.
Ah, okay.
You see, we have beta, this parameter related to the central charge, and here the spectrum is not invariant and the beta goes to 1 over beta because it's not symmetric and in exchange of the 2 Katz indices.
Thanks.
Okay, so the reason why these models look so similar in 2 dimensions is because all of them can be formulated in terms of ensembles of non-intersecting loops, as I will soon explain. And so it's not just the spectrums which look similar, it is the correlation functions. So for example, you could consider the field V20, the non-diagonal field V20, which in fact is present in all of these models. And you could consider 4-point functions of this type. And among solutions of crossing symmetry, you will find solutions that in fact are relevant for all three models. So the same function of Z, if you want, the same correlation function, can be interpreted in 3 different ways depending on the model. On the other hand, you can even take some fields from some models, like this V1/0, which only belongs to the ON model, and then you can mix it with a field VP01/2, which only belongs to the Potts model, and you will also find solutions of crossing symmetry. Then you can't interpret it in any one model, but you can interpret it in, let's say, the general extension of these models, which includes all of them. And you can even write correlation functions here with arbitrary diagonal fields, VP1, VP2, with P1 and P2 arbitrary complex numbers, if you want. So this belongs to no model at all, these fields, but these correlation functions you can also compute, you can also bootstrap, and again, it belongs to some extension of all these models.
Sorry, is it possible to do the following exercise? You have this extended spectrum, which just came from imposing monodromy on the plane, and then ask yourself which subsets are modular invariant. Is that a classification problem that is tractable?
Well, it has not been solved, but I'm not sure if it's tractable. I don't know.
Thanks.
Okay, but I'm not sure modular invariance is really the right question here, because I mean you can think starting from the Ising model, for example, for the minimal model. So you have these 3 fields, 1 sigma epsilon, but then you could start adding a disorder field. So this would break modular invariance, but still it's perfectly consistent. And you can add much more than disorder fields. In fact, you can view the Ising model as essentially Q equals 2 case of the Potts model, where you have infinitely many other primary fields here, which describe non-local objects in this Ising model. And so you don't necessarily want to stop at the modular invariant spectrum like that. You can always extend the model. So I would like to promote the idea that what really matters, what's fundamental, is the set of correlation functions, solutions of crossing symmetry. And then the rest, I mean, including these models, are just, if you want, interpretations of these correlation functions. Things that are built on top of these fundamental objects. Okay, so now let's be a bit more concrete about these models and why they can be formulated in terms of loops on a lattice. So let's start with the ON model. Well, I won't do them in detail, but maybe in the ON model I can be slightly more specific. So the ON model is a model of spins, vectors. Well, let me call them SI, which belong to R to the N, and which live on a lattice. So it's convenient to have a honeycomb lattice. So let's have this honeycomb. So at each vertex of the lattice, you have one of these vectors. And then let's write the energy of a configuration as the sum over neighboring points of some function 1 log 1 plus k si scalar sj. Okay. So okay, the log may be a bit disturbing, but it's just a technical convenience why we write a log. It does not matter very much, but I mean by universality it will not matter in the critical limit. And then you want to compute the partition function by summing, integrating over all possible values of these spins, and integrating what? Integrating exponential of the energy, basically. And when you do that, you use a kind of Wick theorem to contract the vectors with themselves to do this integral. So basically, and this amounts to drawing some bonds on this lattice. For example, in this configuration, here I'm just saying that I'm integrating something like, so this is 0.1, 0.2, 0.3. Here I'm considering S1 scalar S2 times S2 scalar S3. So I'm integrating this over S2, let's say. Because for each of these factors, 1 plus k size j, I have to choose whether I consider the term with 1 or the term with an interaction. But to have a non-zero result, I need an even number of these S2s. I couldn't have a bond here in the sense of having S2, S4. I mean, this is forbidden because if I do that, just the odd number of S2 will make the integral 0. So let's not have that. And this means essentially that when I draw these loops here, they will always be non-intersecting, and there will be only a maximum one loop at each passing at each vertex. And so eventually, this model can be rewritten. I mean, this partition function can be rewritten as a sum over configurations of loops, of non-intersecting loops. And what's the weight of a configuration? Well, in fact, it depends on k. So there is a factor k times the number of occupied edges. But most importantly, when you close a loop, essentially you get a factor which is the trace over this vector representation of the identity, which is n. So you get a factor n times the number of loops. A bond be shared by two loops? Well, that's, I think by convention, that's forbidden. For us, the meaning of a bond is just that that these terms are present. So I draw a bond between 1 and 2 if I have this term in my path integral, S1 scalar S2.
And you cannot have it squared?
No, precisely because I put a log here. So when you take exponential of this, you get just a product. So z, if you want, is the integral of a product of 1 plus k si scalar sj. So it appears only once, I mean, or not at all. But okay, you could, if you don't want the log, you can remove it, and then it just becomes more complicated. But the critical limit is the same. Okay, so this in this formulation, in terms of loops, now n can be any complex number. So that's the big advantage. And k is not really a parameter of the model, because to go to the critical limit, you have to fix k to the critical value, basically. So you have some critical value, k equals kc of n, which is something like 1 over square root of 2 minus square root 2 minus n. So it's the only parameter of the model is n. Okay, so this is a quick reminder of why the ON model is in fact a model of loops. And then for UN, it's almost the same. You have complex vectors, which just means that loops now become oriented. And also neighboring loops need to have opposite orientations. And the Potts model now Well, the POTS model is a model of clusters, so that's slightly different. So you have, let's say, a square lattice, and each node has some discrete variable which takes q values. And then basically what you want to do is to connect the nodes where this variable is the same. So let me connect like that. And let's say this is a cluster, the cluster of nodes where this variable takes a certain value. But then you can reformulate it in terms of loops because you are in 2 dimensions. To do that, you just have basically to draw a loop around the cluster. And so yet again, a loop model. Okay, so now if you agree that we have loops, let's consider correlation functions in terms of loops. So we already know more or less what is the partition function. So the partition function is the sum of n to the number of loops. And then we want to modify that by adding punctures where something can happen. So some punctures z1, z2, zn. And by something happening, I mean that these punctures can modify the weights of loops. So if my loop is contractible, if there is no puncture inside it, it still has weight n. But you can also have loops that go around some puncture or maybe around a number of punctures. And now we can decide that they will have a different weight, these loops. So how can the weight precisely depend on the position of the punctures? I mean, you can't do anything you like because you have to preserve conformal symmetry eventually. So the weight of a loop, W of L, so let's say this is a loop L, well, certainly it can depend on which punctures are inside or outside it. But it could be, you could think we would do something maybe even more specific. Let's say we have 4 punctures here. The weight could depend on the topology of the loop. So, for example, you have this loop here, which goes around puncture 1 and 2. So let's say this is 1, 2, 3, 4. But this loop, well, this loop had a different topology. I mean, on the sphere, they are not topologically equivalent. But still, they go around the same punctures, 1 and 2. So they separate 1 and 2 from 3 and 4. So do we allow this loop to have a different weight from this loop? Well, in fact, no, we don't. And we don't because we would also like our correlation functions to be single-valued. So this loop is obtained from this one by taking a monodromy of the point 1 around the point 3, let's say. And so we want these 2 loops to have the same weight. And this is why basically this model is, I mean, these weights are not functions of the topology, they are functions only of combinatorial properties of loops. And by combinatorial, I mean which punctures are inside or outside. And therefore, we will have, in fact, a finite number of possible loop weights. So if, again, I take my sphere with 4 punctures, well, how many possible loop weights do I have? Or, in other words, how many combinatorially inequivalent loops can I draw on this configuration on the sphere? Anyone has an idea? Well, anyone thinks it's less than 5? Oh, no, but more than 5? 6? Okay, so let's start drawing and see if it's 6. So which loop do we start with? A loop around 1, for example. So let's say this loop has weight W1, right? So we can do this also a loop of weight W2, W3, W4. Well, we already have 4 possible weights. Okay, we also have the empty loop, right? We still have this one which has weight n. And then we could have this thing. So this is what I would call a S loop, WS. But I can also have a T loop, right? WT, or a U loop, WU. So in fact, we find 8 possible weights. 8, which is 2 to the 3.
Sorry, why W, the single loop that goes around on a single puncture, they all have different weights, but the S loop does not depend whether you pick 1 and 2 or 3 and 4?
Right, so we are in the sphere, so it's the same to go around 1 and 2 or 3 or 4.
On the sphere, I see. So there's no other points around, there's only these 4 punctures, okay.
Yeah. And then you could complain that we wanted our loops to be non-intersecting. And here, if you have an S loop and a T loop, they have to intersect. But this only means that you can't have both of them at the same time. So you have to choose. In a given loop configurations, you can have S loops or you can have T loops. You can't have both. Okay, so this is one type of punctures, which we could call the weight-changing punctures. Now there are other types of punctures we can draw where loops can end, actually. So I don't want just closed loops, but I want to allow open loops. So let's have a vertex here, and let's say this vertex has some valency. So valency 3, for example. This just means that 3 loops will end at this vertex. Okay, now, in general, I want to call the valency 2R, just because it will later correspond to the first Katz index R. So R is a half integer now. And of course, the sum of R should be an integer, because eventually every open loop must end at some vertex. So these are, let's say, loop ending punctures. And if I have some vertices, well, again, vertices of valencies, let's say 3, 1, 2, and 0. So valency 0 is this weight-changing loops we had before. Then I can draw, I have to relate this I have to relate these vertices using open loops. And let's do it in all possible ways. There are not so many. Oops. So then we have this one. Yep. And finally, we have a disconnected configuration, which is this, oops. Oh, sorry, it's up, and here, up. So these are all the possible ways to connect these 4 vertices with open loops. And okay, so maybe you want to have this thing, a small loop.
Yes, a small loop.
Well, in this case, we consider that this vertex, in fact, has valency 1, because this small loop, it can get very small and be pulled inside the vertex if you want.
Sorry, but what is the prescription then? What sort of configurations are you summing over?
So we are summing over all configurations of open loops, but we are forbidding loops that can be pulled inside a vertex.
I see.
And also, again, we are considering only the combinatorial properties of these configurations. I mean, we are not considering them different if they just differ topologically.
Okay, sorry. So these different configurations that you draw on, you're saying they would be like different 4-point functions.
Right. So they are different. They are all different combinatorially. So you can, for example, you can distinguish this and this by saying that here this vertex and this vertex, the vertices 1 and, well, sorry, this is 0 because it has valency 0. So the vertices of valencies 1 and 0, here they are separated, but here they are not separated. So
no, I can see that they're different topologically. I'm just asking, I agree that these are different pictures. Like, why are they physically important? Like, are you considering different 4-point functions which only allow these configurations, or?
Yeah, so I want to claim that each of these combinatorial maps, as they are called, will give rise to a different 4-point function.
Okay.
And in fact, this is just because I'm allowed, when I sum over all configurations, I can restrict to the configurations whose combinatorial properties are given by this map, basically. So all configurations such that 3 is connected twice to 2, and well, which has this topology, if you want. And if I do that, I'm not breaking conformal invariance, and therefore I get some conformal invariant Z, which will then correspond to a correlation function and a solution of crossing symmetry. And also, it will be single-valued. For example, I mean, it's single-valued because in this sum, I'm also summing over configurations like that, right? I mean, these two would be topologically different, but they are in fact, I'm identifying them. And this will make the resulting correlation function single-valued because it's now monodromy invariant. Okay, so we are still missing one parameter here, which is the second Katz index S. And the point now is that, well, conformal symmetry is conformal transformations by definition preserve angles. So if I want my partition function here to be conformally invariant, I can still have it depend on the angles of open loops at a vertex. So if I take a reference direction now and I measure the angles, theta 1, theta 2, theta 3, then I'm allowed to add some weight, so a weight W, which will be E to the I over 2S sum of the angles. So S now is a new parameter, if you want it, the angular momentum of this vertex. So a vertex, in fact, is characterized by the valency R and the angular momentum S. So the sum here is from 1 to 2R.
Sorry, there's something I'm confused by. You said these pictures correspond to different 4-point functions, not to different configurations that contribute to the same 4-point function?
So I'm saying there are different 4-point functions in the sense of the bootstrap. I mean, they are independent functions of Z, if you want.
But then I don't understand the labeling, because I would think if they're different 4-point functions, they're 4-point functions of different operators, but your label R and S only seem to care about what sits at point 132 and not distinguish between these 4 pictures. Is there a label? Is the conformal dimension should depend on which of the 4 pictures you pick, and I don't see it there.
Right, so, okay, so you're worried that if I write a 4-point function, let's say V1, V2, V3, V4, you expect this object to just depend on the fields and not on some extra information, which is my combinatorial map. So I'm telling you that, in fact, this quantity also depends on my combinatorial map. And I'm also telling you this is what you would expect even in the ON model, for example, because in the ON model or in any of these models, in fact, your vertex operators here, your fields, they have an extra, let's say, ON index. So, for example, they can be ON vectors. I mean, the field 1 half 0 is an ON vector. So it has an extra ON index I. So eventually you'll have dependence on these indices, and that's why you expect to find several solutions.
We could interpret these as tensor structures in the ON space.
Right, so the combinatorial maps, in a sense, in a very rough sense, indicate a tensor structure, meaning essentially how you contract these indices. But the difference and the subtlety is that we have loops that do not intersect. So if you wanted to write all possible contraction of indices, you would end up with intersections of loops. But here, we don't allow intersections, and therefore we'll find much fewer solutions of crossing symmetry, much fewer combinatorial maps than you would expect based on just the global symmetry.
Mention the fact that, of course, n is not an integer, so it's a bit hard to interpret this in terms of contracting indices. But
right, but okay, just if you want, the number of tensor structures here is n independent, so it doesn't matter that n is not an integer for that.
So Slava and Damon had the paper on explaining, what ON symmetry would mean for an integer n in terms of some Deligne categories. Can you interpret this set of quantities in their language?
Yeah, so if you want, the claim is that what matters really for the CFT is really the category of representations of ON. Yeah. And this category itself, you can write a tensor product of representations, and the coefficients are just integers, they don't depend on n. So this category, it makes sense for any complex n. So that's how I would interpret this.
Yeah, I understand what I'm asking. Can you make a more precise interpretation in that language of all these different 4-point functions that you're mentioning?
Well, in simple examples, you can. In the case, for example, of a 4-point function of these vector fields, V1 have 0 in the ON model. Well, on the one hand, we have 3 combinatorial maps. So each vertex has valency 1. So you have 3 ways of connecting these vertices, right? So, and you find 3 solutions of crossing symmetry. And on the other hand, you can, these are the same. I meant this thing. On the other hand, you can relate these solutions directly to tensor structures here. So VI1, I2, I3, I4. So basically, you have 3 invariants, so which you can write as V1 scalar V2, V3 scalar V4, V1 scalar V4, V2 scalar V3, V1 scalar V3, V2 scalar V4. And then, obviously, they are related to these 3 combinatorial maps. But that's really the simple case.
But is the statement that this can be done in general, or it's not known?
It's not known, and it can't be done if you want your loops to be non-intersecting. So due to this constraint of non-intersection, you will find much fewer, in fact, combinatorial maps than you have tensor structures.
Well, maybe some coefficients of some tensor structures are 0.
Yes, but the correct interpretation, I think, is that, in fact, the global symmetry of this model is much larger than ON.
All right.
So if you allowed your loops to intersect, it would be ON, but since you don't, it has a larger symmetry.
I see. Thanks.
Okay, so so just to remind you, we have
sorry,
this.
Actually,
oops.
You say it's larger. Do you have an interpretation of what it is if it's not ON?
Yeah, we have an interpretation in terms of diagram algebras, like Temperley algebra.
I see. All right. Thank you.
Yeah. So let's come back to our loop ending punctures, which are parameterized by valency and an angular momentum. And then let me write this z now. Once you add the number of these vertices, what does this z look like? So the z is still a sum of a loop configurations, but now each configuration may have a different weight. So first you have a product over all the closed loops. So L is a closed loop in the configuration. Oops. And each closed loop has a different weight, W of L, depending on which punctures are inside or outside this closed loop. And then you have also a product of vertices. And each vertex now has a weight. So a vertex of angular momentum S has a weight which depends on the loop configuration, which depends on the angles of loops at the vertex. So something like a weight depending on the angles. And you expect then that in the critical limit, this corresponds to a correlation function, so a product of something like that in the CFT. So this should be single valued as a function of the positions. This should be crossing symmetric, of course. So you can try to compare it to the solutions of the Bootstrap. But I still have to justify the relations between the parameters. I mean, here I have indices R and S, which, I mean, I'm using the same notations as the Katz indices, but why do they correspond to Katz indices?
Sorry, I missed something simple. So this is a correlation function of only non-diagonal fields, or do the degenerate fields are in some sense contained here already?
Well, the diagonal fields are contained implicitly, because I can always, a diagonal field I can always write as V0 to beta P. So just for simplicity, I'm...
But it's not just that it's diagonal, it's also degenerate, right?
No, it can't. It does not have to be degenerate. It can have any momentum.
But don't we have two, in the ON model, I thought you told us that we have two kinds of fields, the non-diagonal ones, and perhaps the diagonal are a special case of those, but also we have degenerate fields.
Right. Well, in fact, in the ON model, we'll see, I mean, the degenerate fields are essentially trivial. You have the identity which does nothing, but all the others have the same weight as the identity, so they do nothing as well.
I see.
Sorry, so you can...
How is that possible? Sorry, the conformal dimension is not 0.
Right. So, in fact, we don't know exactly how this happens, but there is more in terms of parameters. You see, in the CFT, we have much more freedom than in the loop model. And we interpret this as saying that in the loop model, if you go too far in parameter space, you could stop being critical. So if you take a diagonal field and try to have a large momentum to go to this V1 to this P13, you could break criticality.
But this is just local insertion. How can that break criticality? Does it?
Right. So I'm not sure. I mean, this is what we know happens at the level of the parameter n, right? So you can start from n in -2, 2, and then if you start to go out in the complex plane of n, at some point you'll reach.
Yeah, that doesn't surprise me. But for any given value of n, don't you have a P13 that is legitimate?
Well, you do, but we are not sure how this is represented in the loop model.
Okay.
Because now I will compute the weight, if you want, the weight of this as a function of P, and we'll see that the weight associated to P13 is the same as the weight associated to P11. So apparently, they are the same at the level of the loop model.
I see. But so when you told us that people computed the modular invariant partition function, the degenerate fields were not there?
No, they were there, in fact. So the modular invariant sees them indeed. The partition function sees them. Yeah.
I mean, okay. This seems like a very impenetrable mystery to me, but okay.
Right. I mean, there are still mysteries in this story. Yeah.
Thanks.
Sorry, can I ask one question? So this R parameter corresponded to the valency of the vertex?
Right.
But so you're computing this on the lattice. So say if you have a honeycomb lattice, can you have valences greater than 3?
Right. So that's a very good point. So how do we do in a honeycomb lattice to have an arbitrary integer as the valency of a vertex? And the answer is it happens only in the critical limit, if you want. So in the critical limit, we could decide that our puncture, what I call a puncture, it could be made of several vertices. We just shrink to the same point when the lattice becomes very large. And if I have enough vertices, then I can have as many legs as I want.
And the same goes for these angles that you have to consider.
Right, so the angles, again, indeed, it looks like the angles can only be multiples of 2 pi over 3. So, but I could decide to measure the angles. Well, let's say on the square lattice, I would measure the angles by taking a large enough circle around this point, and then I can have arbitrary angles.
All right, thank you.
Okay, so how do we map the parameters of this lattice model to the parameters of the CFT? So this is a mostly heuristic argument, but I think it gives unique and correct answers. So first, we want to map the indices R and S, well, of the non-diagonal fields. I mean, discrete parameters are easier to map because we know that if you want Katz indices R and S, well, they are such that R is half integer and RS is integer. And now if you look at puncture, the indices of puncture, also R and S, well, they also have R half integer. And also I forget to mention that some of the R is integer. Here also sum of R is integer. Well, so this R obeys the same constraint. So it's tempting to identify the R. And then R times S, what is R times S? Well, in fact, you can see that R times S, here is the conformal spin, and here it's also the conformal spin. Because the weight of my puncture was just e to the I over 2s sum of thetas. But if I do a rotation of all the angles, theta goes to theta plus delta theta. Then, under this rotation, WRS picks a factor e to the I RS delta theta. And this shows basically that R times S is also the conformal spin. And also it has to be integer, of course, because a rotation of 2 pi does nothing. So therefore I have to identify R times S with R times S here, and if we agree to identify R, we have to identify S as well. And so therefore we identify puncture here with the non-diagonal field with these Katz indices. Okay? So if you're following me from this, we'll try to deduce the identification of parameters for the diagonal fields. So we have a diagonal field VP, and the trick is that VP we know is the same as a non-diagonal field with parameters 0 and 2 beta p. So what we want to know is the weight here, W, which should depend on P, of a loop going around this puncture. And what we'll do is to take this formula for the weight, apply it to these indices 0 and 2 beta p, but for a specific angle. So since we're interested in a closed loop like that, the angle, well, what should be the angle? Well, I want to claim the angle is 2 pi. So we'll say that W of P should be E I over 2 S which is now 2 beta p times 2 pi. Well, does this look correct? Well, oh, it's almost correct. The point is, I mean, why do I choose 2 pi? I mean, my loops are not oriented, so it could as well be minus 2 pi. So in fact, you're doing this, minus 2 beta p times 2 pi. And what you get is 2 cosine 2 pi beta p. So that's the weight, the loop weight associated to a puncture of momentum p, to a primary field of momentum p. And that's where you can see that the primary fields of momentum p11 and p13 in fact have the same weight, which indeed looks a bit mysterious. So, and then we are in the position to deduce the relation between n, the n of the ON model, for example, the n which is the loop weight, and the central charge. So let me rewrite this formula, 2 cos 2 pi beta p. So now we want to compute the weight of an empty loop. An empty loop is a loop, if you want, where you have here a trivial field, so the identity field, V11, degenerate. Therefore, I expect that n equals W of P11, which is minus 2 cos pi beta squared. And let me remind you that beta now is related to the central charge as before. And so, therefore, we have related all the parameters of our loop model to parameters of the CFT. Okay, so are there questions about that? Well, if there are no questions, I mean, what remains to do is to relate the specific correlation functions, because now we have all these combinatorial maps on the one hand, and we have a set space, a linear space of solutions of crossing symmetry on the other hand, and we want to know which map corresponds to which solution of crossing symmetry. And I can't give a complete answer to this question at the moment, but I can do it in some examples. And so let's consider some map. This one, for example. So we know already that this could correspond to a 4-point function of the type V3 half 0, V1 half 0. Sorry, oops. Here, well, it doesn't have to be V1 0, it could be V1 1. And here some field VP. Okay, and then the idea is still that we have this relation between valencies and between the first Katz index. And this relation should also be true, so not only for these external fields, but also for the internal fields. So what does this mean? So this means that if I want to decompose this 4-point function, let's say in the S channel, I want to cut my diagram like that. And here I'm cutting a minimum of 2 open loops. And therefore, I'm calling this number the S-channel signature, sigma S, which is half the number of loops I'm cutting. So this is 1 in this case. And then we could do the same in the T-channel. So in the T-channel, we are cutting 3 open loops. So the T-channel signature would be 3 halves. And in the U channel, well, in the U channel, we are just cutting one loop. So sigma U is 1/2. And therefore, the signature, which is the list of these numbers, is 1, 3/2, 1/2. Now, at the level of Bootstrap, the interpretation is that the spectrum of this 4-point function in the S channel will be the set of non-diagonal fields, so VRS, where R has to be larger or equal to the signature. So R bigger than 1, so which means R, in fact, a strictly positive integer, and S is whatever it is. In the T channel, the spectrum would be VRS with R belonging now to 3/2 plus an integer, like that. And U channel, well, you can guess. So the spectrum is a bit smaller than what I could get in general. In principle, here I have eliminated the field V1/0 from the T channel. And if you do the bootstrap with these spectrums, then you may find a unique solution, which will correspond to the particular solution of crossing symmetry, which is associated to this combinatorial map, which I'm calling M. But this doesn't work for all maps. I mean, because you can have several maps sharing the same signature. I can give you a simple example. So these two maps here, oops, they are different, but they have the same signature, sigma equals 1/2, 1/2, 1/2. So you're left with a two-dimensional space of solutions of crossing symmetry here. So we don't know the general answer to this question, which solution of crossing symmetry corresponds to which combinatorial map. But what we could do to support numerically this relation is to at least count the number of solutions. So in any case, we tested if you count the number of linearly independent solutions of crossing symmetry, you find that it matches the number of combinatorial maps you can draw. Okay, are there questions on this? Yes. Sorry, I didn't quite get the question. Maybe, yeah, could you repeat louder?
Positive integer, where the lowest one is just the cut that you're drawing there, but you're saying there's other possible operators in the S channel. How do you draw those configurations?
Okay, so you want me to draw...
so for example, R equals to 2 in this case.
Right, so you want me to do a diagram which would correspond to having R equals 2 field propagating in the S channel, for example, right?
Yes.
Well, okay, so one way, I mean, you can always draw these lines, deform them such that they cut, they would cut your loop here more than twice. So here I have 2 cuts, that's the minimal I can get. But I could deform this to do something like that, right? I would increase the number of cuts. So indeed, that the intuition why the signature gives you the minimum index of a field, but then you have all fields with larger index. Okay. Right, so here, well, again, you do the same game. You try to draw the cuts, and oh, maybe what I wrote is wrong here. Oh, so it's not 1/2, 1/2, 1/2. You mean it's just 1, 1, 1? Oh, sorry. Yeah, you always cut 2 lines. Indeed, you're right. Okay, so now the idea is that for many combinatorial maps, but not all, this prescription here gives us a unique solution of crossing symmetry. And it is these unique solutions that we now want to study. We want to, I mean, using the numerical methods I talked about last time, we want to compute their structure constants and see if we can find analytic expressions for these structure constants. And it's quite important to have this privileged basis of solutions, because if, in principle, you could have, I mean, we have a vector space of solutions. So if we do combinations of these solutions with random coefficients, then this is not likely to give us a nice analytic formula for the structure constants. So on that, I mean, the guess is that with this privileged basis, we'll get indeed a nice analytic formulas. So how do we do that? Well, we take a 4-point function, we consider a given combinatorial map, and we find a unique solution of the bootstrap, which is in fact a collection of structure constants. So US, T, and U channel, parameterized by a field indices K. We divide these structure constants now, these D, which are 4-point structure constants, by reference structure constant. So last time I gave you a formula for the reference 3-point structure constant, Cref, which was a big product of gamma beta functions. And from this you can build a D ref structure constant. For example, in the S channel you get, this is just C1, 2K, C3, 4K over some BK. So after you compute this ratio, you call it small d now. And what do we know about small d? So by definition, by construction, let's say the reference structure constant is a solution of the shift equations. So therefore, dk should be invariant on the shifts. So what parameters does dk depend on? Well, it depends a bit on your map. But we could take a map which is disconnected like that. Oops. So let's consider, for example, this map. So here in the S channel, you can draw an S loop of weight Ws. So this dk, when you do the bootstrap, this corresponds to a diagonal field VPS. And this dk has to depend on PS. But now, because it's a solution, because this is a solution of shift equations, what this means is that dk of PS is dk of PS plus beta inverse. Sorry, this is not very well written. Now, if you remember, Ws was the 2 cos 2 pi beta ps. So the fact that dk is periodic of beta inverse means it's in fact a function of Ws, not just a function of ps, but a function of this trigonometric quantity. So, okay, so this reasoning works for this channel momentum PS, but the assumption, now the conjecture, is that it works also for n. So a priori you could expect decay to be a function of the central charge, to be any function of the central charge, but now we are claiming it depends on the central charge only through n. So n, which is still minus 2 cos pi beta squared. And we are further conjecturing that in fact this decay is a polynomial in Ws and in n. Okay, so this conjecture is well, kind of natural from the point of view of the loop model, because in the loop model we are basically taking a sum of products of these weights. So everything is polynomial in the weights in the loop model. But in the CFT, it doesn't have to be the case. After you take the critical limit, I mean, a limit of a polynomial of a large degree, it's no longer polynomial a priori. But for this ratio here, decay, we found numerically that it's actually a polynomial. So now I propose to write explicitly some examples of these polynomials. So in specific cases. So let's take a 4-point function. Well, let's do the simplest 4-point function of non-diagonal fields. So this V1 half 0 4 times. And let's take this combinatorial map. So we have here an S channel loop of weight Ws, which means that the S channel spectrum is just the VRS union. Well, you need some diagonal fields, so all the VPS plus J beta inverse. Okay, and so the T channel spectrum, for example, will just be the set of VRS Okay, so we solve crossing symmetry with these spectrums here. And now you find, if you do that, you find the following structure constants. So you find ds for a diagonal field here. So that's 1. That's our normalization condition. You find ds 1, 0 equals 0. ds 2, 0 equals n squared minus 4. ds 2, 1 equals minus n squared minus 4. Sorry, so here I'm writing only fields with even spins. I mean, the odd spin fields in this configuration vanish. So I'm not writing them. So 3 ds 3, 0 is minus 8 n squared n minus 2 squared n plus 2. 3 ds 3 2/3 equals 4 n squared minus 1 n squared minus 3 n minus 2. Okay, well, now you could start to worry that I've claimed that this ds would depend on ws and the momentum, on this momentum, and so far nothing seems to depend on it. But that's only true for r less than 3. So the last example I want to write is the D40, which now will depend on WS. So let me, oops. I fear that I'm out of space, so I'll try to write D40 in a box here. DS40 equals n squared, n minus 2 squared. No, it's a cube, sorry. N plus 1 squared, n plus 2 times. Now we have our dependence on WS, which is linear, n plus 2 squared, n minus 1 squared, plus 2 n to the 4th, minus 6n squared, minus 8n plus 16. Okay, so these are examples of this type of results, which are analytic formulas, which we just inferred from high precision numerical results for these objects. So, well, since it's polynomials and it's polynomials of degrees that are not terribly high, it's not super difficult to interpolate them from the numerical results by just computing this numerically for various values of the parameters n and ws. Yes?
Do we have guessed at least the degree of the polynomial from the weights? Is there some pattern in the degree in n and ws?
Yeah, that's a very good question. And well, I don't really know, because what we did in practice was to just get a bunch of these polynomials and then guess the degree based on the pattern we see. But indeed, it would be very interesting to guess the degree and maybe even to guess the polynomials themselves from some pattern. From some patterns of configurations of open loops. So this does not look hopeless, because these are polynomials here with integer coefficients. So maybe these integer coefficients have some combinatorial interpretations. That's the hope, but we don't know that. Well, yeah, but okay, you have to train it on a large enough sample, because, for example, if you do these simple examples, you find integer coefficients, but for more complicated examples, the coefficients are no longer integer. In fact, the coefficients can be trigonometric numbers. So typically, they are of the type cosine pi times some angle, some rational number. Well, okay, these trigonometric coefficients are not surprising, because they should come from the phases, from the loop weights, which were, if you remember, we had this WRS, which was exponential I s over 2 some theta. So that, morally speaking, that should be the origin of these cosines in the polynomials. Okay, so one
question.
Yes.
Here. So, did you try also complex n when you did the numerics?
Yes. Well, in fact, it's sometimes easier to have complex n.
I see.
So nothing really prevents it. Well, for the bootstrap, you can take any complex n, basically. In the loop model, on the other hand, you can't, because you would be get outside the region of criticality. So, well, there is a region. I mean, you can still take it complex, but at some point you will reach a line where, when an operator becomes relevant, and then the model can stop becoming critical. Okay, so I think one advantage of having analytic formulas is also, if you want to take, let's say you want to study specifically percolation. So for this, you need a very specific value of n. Well, rather it would be in the Potts model. So a value of q, of the parent of the Potts model. You would need the central charge 0. So here at central charge 0, the representation theory of Virasoro becomes more complicated with logarithmic representations. The bootstrap becomes harder because the blocks have singularities, so everything becomes harder. But if you get an analytic formula for your structure constant, then it's quite easy to take a specific value of n now. So in this sense, bootstrapping the CFT at generic complex n could even help us, even if our aim is just to study a very specific model at a very specific rational value. Okay, so I want to give a second example of this type of result by looking at a completely different 4-point function now. If there are no questions on these formulas, or maybe someone spotted a mistake. Yeah. So let's consider a 4-point function of 4 diagonal fields, VP1, VP2, VP3, VP4. So in this case, I mean, it looks a bit unphysical because these fields don't belong to any of our models. Well, in fact, that's not quite true. I mean, if you take the values p, for example, equals p0 1/2, I mean, you had diagonal fields of this type in the Potts model. And if you take 4 diagonal fields of this type, you get 4-point functions that, in fact, compute for you the so-called cluster connectivities in the Potts model. So the Potts model is, at the level of statistical model, is, I mean, you draw these clusters which tell you which pins have the same values, which variables have the same values. And then the question you can ask is whether these 2 points maybe are in the same cluster, while these 2 points are in some other cluster, or maybe 4 points are in the same cluster here. And to compute the probabilities of these things, well, you have to study correlation functions of this type, because in fact, they tell you if the point Z1, let's say, so this field here with this dimension tells you if your point Z1 belongs to a cluster, essentially. So this dimension is quite special. The corresponding weight here is just 0. Okay, so now the corresponding combinatorial map is quite trivial. It's just 4 punctures with valency 0. And the question is, well, can we bootstrap that? So the idea is that we can have here S loops here with weight WS. We can also have T loops, and we could also have U loops, WT. So we expect this 4-point function to depend on all these parameters. So it should be a function not only of n, but also WS, WT, WU. Well, in addition to, of course, W1, W3, etc., W2, W3, W4. So a function of 8 variables, in fact. So, well, in fact, you could be a bit skeptical that here I'm not just introducing a dependence on a discrete combinatorial map in my function. I'm even introducing a dependence on 3 continuous parameters, W, S, T, U, which don't depend on these 4 fields, right? I mean, a priori, a 4-point function of these fields should just depend on the central charge and on the parameters of the fields. So in CFT, it's not so clear why you have dependence on these extra variables. But a possible interpretation is just that you are not really computing a 4-point function, you are computing a 4-point function in the presence of defects. Well, not quite topological, but combinatorial defects. For example, this, I would say, I would consider as a defect of parameter WS corresponding to the fact that the loops in this S channel have this particular weight. So that could be the CFT interpretation of this parameter WS. Okay, so now if you do the bootstrap for this 4-point function, you find a unique solution, and you find structure constants which look as follows. So in the S, T, and U channels, for the diagonal fields, we normalize the structure constant to 1. Well, it's already a non-trivial statement, in fact, because, I mean, you're allowed to normalize one structure constant, but I'm telling you that 3 of them are, in fact, 1. And then the 1, 0 structure constants, well, they are WT plus WU here. Well, I'm not writing the other channels. You can guess by permutation symmetry. The 1, 1 structure constants are U minus WT. And the non-trivial thing I will write is the D20, DS20, which now is n squared minus 4. WT squared plus WU squared plus 2WS minus 4 minus n minus 2 WT plus WU W1 plus W2 W3 plus W4 minus n plus 2 WT minus WU W1 minus W2 W4 minus W3. Okay, so this again interpolated from numerical results. It's a bit more work because now you have all these 8 variables, but fortunately these polynomials are not of very high order. Okay, so we have some analytic results of this type. Well, to be precise, we have computed like 235 such structure constants, but the model contains infinitely many, so it's still a challenge to compute all the others. And that's not the only challenge we have. So if we wanted really to solve the model, we would have to compute all structure constants. But that's still not enough. I mean, we would have to do that for all combinatorial maps. But for a number of maps, we don't even know which is the correct solution of the bootstrap. And most importantly, I mean, we would have to factorize the 4-point structure constants into 3 points. Or in other words, to check that OPs really exist. Because, I mean, to solve the model, you should be able to compute n-point functions. And you won't just directly deduce that from some results on 4-point functions. And it's really not obvious how to factorize. I mean, if you look at these formulas, for example, well, it's not clear. I mean, they don't factorize, in fact, or let's say they factorize in as a sum of several factorized terms. I mean, by factorization, I mean factorizing the dependence on 1 and 2 from the dependence on 3 and 4, if I'm in the S channel. So these are the challenges that remain. So, but the formulas, the analytic formulas we have, allow us to conjecture that the models are solvable, even if we are still a bit far from solving them. So, thank you.
Thanks a lot, Sylvain. Do we have questions? Yes?
You probably said this that I missed earlier. When you take, so the loop model has this parameter k and n, and you need to take k to the k critical. If you deform slightly away from that, what deformation does that correspond to in the CFT?
Well, that's V13, so the energy field.
I see. And then another question is, what's the relation between the ON loop model and the ON nonlinear sigma model?
And what?
The nonlinear sigma model.
Yeah, I think they are supposed to be related, but how exactly? Yeah, I'm not sure.
Okay, thank you.
More questions? Okay, maybe I have one final question. You said that you could relate the 4-point function for different models, ON, UN, POTS. But then in the last slides, you just described the pods. So is there a clear going back and forth between ON, UN, and pods in this last formulae that you showed?
Yeah, well, I have focused on simple examples. So if you want a 4-point function which belongs to ON, both ON and pods, you have to use fields that belong to both models. And the first non-trivial field which does that is this V20. But V20, you see, is already pretty complicated. Like it has 4 lines here. So you have, let's say you have 4 vertices like that. And you have to connect them. So you have of the order of maybe 18 possible ways to do that, so 18 combinatorial maps. So your crossing symmetry equation has a space of solutions of dimension 18. And then you may want to interpret that in terms of correlation function of the ON model. But then in the ON model, this field V20, it does not belong to an irreducible representation. It belongs to a rather complicated representation of ON, which in terms of Young diagrams, it's something like this. So it's a bit complicated. And if you, based on ON representation theory, if you look at the tensor structures for this 4-point function, you find 2,862 tensor structures.
I see.
So all of these should be combinations of these 18 solutions, but it's a big mess, right? I mean, and then you can do the same exercise on the pod side, where it's also rather complicated. So we have not tried to do that. I mean, it's just complicated.
I see, thanks. So if there are no more questions, let's go for the coffee break, and we will meet again at 12. Thank you.